So I'm going to talk about synthesizing recursive functions using some intermediate unreality results. And this is joint work with Danielette and Azadeh Farzan, who are also both here at the conference. So you can ask them questions later. And so first, I'm going to talk about the problem setting and then explain how we solve it. So we assume that we have some reference implementation that is a recursive function. For example, we have a function that searches for some element in the list, recursively traversing the list. And we want to synthesize some function that belongs to another, that takes another input type B here, and belongs to a target family of functions. So for example, we want some function on trees that will be equivalent to the function that searches an element in a list. And the last component that the user specifies in our problem is some input constraint on the target family of functions. For example, here we can let the user specify that the tree should be a binary search tree. And so that's also another recursive function. And what we want to synthesize is some function that belongs to the target family of function and satisfies the specification that for any input of type B, if it satisfies the constraint I, then G, the function that is in the target family, is equivalent to the reference implementation. So for example, here I showed you how I would try to synthesize a binary search on a binary search tree. So here I'm going to show you a simple example that I'm going to use throughout this presentation to illustrate the different concept. And the reference function is takes the minimum of a list. So it's a recursive function that traverses a list. And the type invariant says that the lists, so here the target type, input type is the same as the original input type. And the type invariant says that the lists are sorted in increasing order. And now I want to specify what kind of functions I want to synthesize. And here I'm specifying that I want constant time functions on list. Because when I say that g of singleton A is only a function of just A, and g of A followed by the tail of the list L is just a function of the head of the list. So any function that implements U0 and U1, which are my two unknowns in the synthesis problem, will be a constant time function on lists. And you can see that here I have a solution for this problem because the list is sorted in increasing order, so the minimum of the list should just be the head of the list. And so what is our problem here? We're trying to synthesize recursive functions, but we have two unbounded dimensions in the 4x quantification. We have the recursion, so lists can be of any length or trees can be of any depth, but we also have scalar elements, so unbounded integers. Luckily, we have solvers that can solve for these kind of problems. We have syntax-guided synthesis solvers, for example. And so what we're trying to do here is to approximate the problems in 1 with problems in 2 and use a refinement loop to solve the problem. This approximation consists in selecting a set of symbolic inputs T, and instead of the quantification over all inputs of type B, we're quantifying over all the free variables in these terms in the set of symbolic inputs. So if those variables are, for example, of type integer, then we'll have quantifications of our integers, and we can solve for this problem. And we integrate this in a loop with the synthesis oracle, which can be implemented using, for example, syntax-guided synthesis. And then if we have a candidate solution, we need to verify over all inputs of type B. If it's valid, we have a solution. Otherwise, we have a counterexample which we can generalize and add them to T. So this is a symbolic version of the CGIS algorithm, if you know the counterexample guided inductive synthesis algorithm. And last year at CAV, we presented a paper in which we argue that you don't need to necessarily bound everything in this in the symbolic inputs. You can leave some unbounded variables, and then apply a procedure that eliminates the recursion not in the input term, but in the constraints that we compute from these terms. And this technique shows a great improvement over both a concrete counterexample inductive synthesis and a symbolic CJs that I just presented. So we want to use this now to solve our problem. And we have our recursion skeleton, and if we take, for example, an input X that is the singleton list A, then we have this constraint and there's no problem. The singleton list is always sorted, so the invariant is true, and U0 of A is a constraint that is in the theories I can solve with syntax-guided synthesis. And then if we take a symbolic input X, A followed by a list L, we have this constraint, but with the work that we presented last year, we know that we can syntactically eliminate the call to lmin by replacing it by a single scalar variable. The problem here is that we don't know what to do with the invariant here, and a syntactic solution that eliminates the recursive calls would not be sufficient. We're trying to infer some predicate that would summarize the semantics of the predicate that says the list AL is sorted. And we need to synthesize this. So now our new approximation parameters are not just a set of inputs T, but also a set of predicates P. And the constraints are formed by adding the condition that comes from this set of predicates before the constraint that we compute as we did before. But how do we learn these predicates? So that is where having unrealizability will help us. And I'll explain what spurious unrealizable approximations are. So the key component in this procedure is the unrealizability checker. And we want to check that there is no function that can possibly satisfy the set of constraints we have. And we designed a technique that we call functional unrealizability and focuses on type of constraints where we have some unknown function f that takes some input and has some output. And most of the all the constraints in the problems we have are of this kind. And intuitively, you want, if you know that there's two outputs for a single possible input, you know that there's no possible function that can satisfy this. So if I have models M1 and M2 that map the inputs to the same value, but map the outputs to two different values, then I have a proof that I cannot satisfy this constraint. And in our example, the constraint f of a equals min of as is unrealizable because I just need to give two different values for s, and then I have something that tells me that f of 0 is -1, but also something that tells me f of 0 is 0. So I can't possibly implement this function f. So now that we have an unrealizability result for our approximation, what do we do about our more general problem, the original problem with the recursive functions? So we need to check whether this example, this unrealizability witness is spurious or not. Intuitively, we want to know whether the values that we have in the witnesses in the model corresponds to value that can exist in the more general problem with recursion. And in the example, we had a model M1 that assigns the value -1 to S. And if you remember, S was replacing the recursive call minimum of the list L. But we also have the invariant that tells us that AL is sorted and that A is 0. But there's no list that can be sorted, and the first element is 0 and the next element is -1. So we have a contradiction here. So with this contradiction, we're going to try to synthesize predicates that can eliminate this possibility. So we want to learn from these spurious witnesses of unrealizability. And intuitively, the predicate synthesis procedure takes these spurious witnesses as negative examples. So the predicate must be false on these inputs. And we have a counterexample guided loop that learns positive examples and synthesize a predicate that classifies the negative and positive examples. So in this case, we had the example 0, -1, which was our spurious unrealisability witness. And we have the example 0, 1, which is some positive example that we learn. And one solution is the predicate that says A is less than S. And you can see how it corresponds to having discovered that in a sorted list, the minimum of the list, of the tail of the list, is larger than the head of the list. And once we have this predicate that we add into our approximation, we get a realizable constraint and we find the solution. So how does this fit into our algorithm? We had initially this symbolic CGIS algorithm that is learning realizable problems, but now we have also this other part that learns unrealizability. So if an approximation with P and T is unrealizable, we get an unrealizability witness. And then we can check whether this witness is spurious or not. If it is not spurious, then we have proved that the problem, the recursive problem, is unrealizable. And that's one other advantage of this method. Now we can also do both unrealizability and realizability. But if it is spurious, then we need to synthesize these predicates that will put into the approximation and that will eliminate these spurious inputs. And we add this predicate to P. And the algorithm can take loops alternatively from both sides. So we can add terms to T and then learn that, oh, we got an unrealizability witness, then we need to refine the predicate that corresponds to the new term, and so on. So both loops work together to find either of those answers, either a solution or unrealizability. And we evaluated this method implemented in a tool on a set of 140 benchmarks that are about synthesizing recursive functions with various type invariants, for example, binary search trees, sorted lists. And if we have both realizable and unrealizable examples. And if we just use CGIS without unrealizability, we solve only 70 benchmarks, which are realizable benchmarks. And we can add our functional unrealizability checker that will additionally solve 25 other benchmarks that are unrealizable. So the answer here is, oh, there's no solution to this problem. And finally, if we combine the two loops together with the unrealizability, we solve an additional, we solve 137 benchmarks over the 140 benchmarks. We can also compare the two techniques, so symbolic CGIS with unrealizability checking and the combined loops C2GIS over the benchmarks that are both solved. And here there's a more nuanced result where the performance, the runtime comparison is not clear. We have, on one hand, if we use symbolic CGIS, we need to learn more terms in the input set T. But on the other hand, if you use C2GIS, then you need to learn those predicates, and it takes time. And so there's a balance between the two methods. So the takeaways of this talk is that we have designed a simple technique to check for unrealizability for problems that are typically solved by CGIS, in which we use this idea of functional unrealizability. And if we just add this to an existing algorithm, it solves a class of unrealizable benchmarks. But we also have a new synthesis algorithm, and we extend CGIS with results on unrealizability. And it can help in, for example, designing approximations that are not necessarily over-approximations of the problem. And in this case, it allowed us to use partial bounding in a setting where it's not an over-approximation, and learn these predicates that summarize the invariant. And all this has been implemented in a tool Synthesize that is available online. And so thank you for listening, and let me know if you have any questions.
Hi, very nice work. So I have two questions. One is, how do you synthesize the refinement predicates, and what is a good refinement predicate? So maybe I can ask you this one first.
So the predicates, we use syntax-guided synthesis, and we have the default grammar for Boolean predicates in linear integer arithmetic, and we give input. So the unrealistic example correspond to input-output examples, and so any syntax-guided synthesis solver can be used.
Thank you. So my other question is, so like you stated this part that I don't understand, that basically approximations are not over approximations or under approximations. So do you know what they are exactly? Like in what sense they're approximating? And the other question is like, what does this mean for the progress measure of your algorithm? Like, is it sound, complete? When is it sound? When is it complete?
So it's hard to, so when it is unrealizable and we have a realizable problem, so it is an under approximation in the sense it eliminates all possible solutions. And then once you learn the predicate that enough to synthesize a predicate that eliminates the spurious witnesses, then you have another approximation. So every time we take the loop on the top, we have another approximation, and every time we take the loop at the bottom, we have a under approximation in the sense that it eliminates, like there's no solution.
Let me ask a question that might be related. If I understood correctly, is it true that your unrealizability checker relies on a sufficient condition for unrealizability? Mm-hmm. That if two inputs that are equal produce the same output, then there is an issue. Mm-hmm. That's a sufficient condition. Have you, what impact does that have on the whole loop? It's not necessary and sufficient, right, for unrealizability?
So it's a sufficient condition, but our unrealistic checker is definitely not complete. But given the problem setting we are in which we have these equations, we saw that for all the benchmarks we considered it was enough to prove unrealizability, but we can also construct benchmarks explicitly that will show the limitations of our checker.
Thank you. Any other questions? All right, let's thank Victor again.